Okay, so welcome to this next video in which we are discussing how to measure calcium concentration using Fluo-4. Okay, so just to remind you where we've got to at the moment. What we've done is we have some test solution which contains dissolved calcium ions, and we want to know what is the concentration of calcium ions in that solution. Okay, so what we have done is we've added some of this Fluo-4, okay, and basically what will happen is some of the calcium ions will bind to the Fluo-4, and basically when you have Fluo-4 bound to calcium, the fluorescent properties of that Fluo-4 calcium complex are far better than just the Fluo-4 on its own. So basically what will happen is the fluorescence that you will get off this calcium mixture with Fluo-4 will be greater than if you just had the solution containing only the Fluo-4. So what you do is you measure the fluorescence coming off. So you shine some blue light of wavelength around 490 nanometers at our solution, and you'll get green light coming off. You will measure the intensity of that green light. That's what F is, okay? So this is the fluorescence coming off our test solution. You then add some Bapta, okay, which is a calcium chelator, which will basically nick all of the calcium and bind the calcium to itself, so that there is no calcium left over in the solution, and therefore there's no calcium to bind to the Fluo-4 molecules. So now all of the Fluo-4 molecules are by themselves in that solution. Okay, that means we have got the absolute minimum fluorescent properties that we could have for that concentration of Fluo-4, basically. What we will then do is shine blue light of the same intensity as before at this solution, and we'll get less intense green light coming back. Okay, we will measure the intensity of that green light, we'll call it Fmin. Okay, finally what we'll do is we'll completely saturate the Fluo-4 molecules with calcium. So we'll put in loads and loads of calcium chloride, firstly to saturate the Bapta molecules, and then to saturate all the Fluo-4 molecules. Okay, so that every single Fluo-4 molecule in that glass, at least to all decent approximations, has a calcium molecule bound to it. Of course, there might be one or two, that don't have Fluo-4, but that's negligible. Okay, right. Basically, all the Fluo-4 molecules will have calcium bound to them, and therefore the fluorescent properties of that concentration of Fluo-4 now are at their maximum. So we'll shine the blue light at this solution containing Fluo-4 molecules which all have calcium bound to them, and we'll get some large intensity green light coming back, and we'll call the intensity of that Fmax. Now my claim is that we can now work out what the free concentration of calcium is. So firstly, let's see if we can write F, the fluorescence of the calcium solution when you've just added the Fluo-4. So no Bapta and no extra calcium has been added yet. Okay, let's see if we can write that in terms of Fmin and Fmax. So basically, if I draw a picture, okay, so we're drawing the scenario where we measured F. Okay, so we have our original concentration of calcium in this solution, and then we have added our Fluo-4. Okay, now some of the Fluo-4 molecules will have calcium bound to them, and some will not. Okay, so the ones which do have calcium bound to them, those will be fluorescing at the higher level, and those which don't have calcium bound to them, those will be fluorescing at the lower level. Okay, so I'm going to let alpha represent the fraction of molecules, the fraction of Fluo-4 molecules which have calcium bound to them. Okay, so fraction of Fluo-4 molecules with calcium bound to them. So I'll just put Fluo-4 calcium. Okay, so what's the answer from my picture here? Well, I've got 5 Fluo-4 molecules in total. Of course, in reality, it'll be far more than that. But just for the basis of this picture, I've got 5 Fluo-4 molecules in total. 3 of them have calcium bound. So what fraction of them do have calcium bound, well, it's 3 over 5, which is 0.6. So that's what alpha means. Okay, so this is the fraction of the fluo-4 molecules that will be fluorescing at the higher level. Okay, the other fluo-4 molecules which don't have calcium bound to them, the fraction of fluo-4 molecules which won't have calcium bound to them will be 1 minus alpha. Okay, so in this case, if we stick in alpha is equal to 0.6, we'll get 0.4, 40%, which is obviously correct. So it's what's left, basically, because obviously the ones which do have calcium bound to them plus the fraction of them that don't has to add up to 1, and therefore we can just get the fraction that doesn't have calcium bound by taking 1, subtract off the fraction which does have calcium bound. Okay, so this is the fraction that will be fluorescing at the lower level, basically. Fraction which fluoresce at low level. Okay, right. So if we want to now know, how do you spell fluoresce? Fluoresce, I'll go for that. Fluoresce at lower level. If we want to now know what fluorescence we are going to get coming off this solution, well, my claim is that it's going to be alpha times Fmax, okay, plus 1 minus alpha times Fmin. Okay, and let me explain why. Basically, if absolutely all of them have calcium bound to them, then the fluorescence that you get is Fmax. We do not have all of them bound to calcium. The fraction that we have bound is alpha. So the amount of fluorescence that we're going to get from the ones which do have calcium bound is going to be alpha, i.e. the fraction of them that is bound, times Fmax. So in this case it will be 0.6 times Fmax. Okay, because those ones will be fluorescing at the maximum rate, but of course this is how much we'd receive if all of them were fluorescing at the maximum rate. So how much are we going to get of that? We're going to get 0.6% of that. Sorry, not 0.6%, but 60% of that. Okay, because only 60% of our molecules have got calcium bound to them. Okay, the other ones which don't have calcium bound to them, they will be fluorescing at the Fmin rate. Now Fmin is what you get if all of them don't have calcium bound to them. The fraction we have that don't have calcium bound to them is 1 minus alpha, so we need to times 1 minus alpha by Fmin, and that's the fluorescence we'll be getting off the ones which do not have calcium bound to them. If we add these two together, then we'll get the fluorescence coming off the whole thing, basically. That's the idea. Okay, so now all we need to do is work out what this alpha is, and this requires a little bit of pharmacodynamics. Okay, so we are going to need to work out something called the occupancy equation. Okay, so pharmacology has an equation that allows you to work this out, basically, and it's called the occupancy equation. And I just want to derive the occupancy equation because I want this video to stand on its own. So I apologize if you already know the occupancy equation. So basically, there is an equilibrium. Okay, there is an equilibrium between fluoro-4 molecules which are free and calcium ions, okay? And the fluoro-4 ions which are free combine to calcium ions to become, let's say, just fluoro-4 molecules with calcium ions bound, okay? And this is a reversible reaction. So let's think about what happens. So if we have our beaker here, whoops, initially what happens is we have some calcium ions in here, which I'll show as the orange dots. And I think, how many should I put in? I'll put in 10. How many have we got now? 10, there we go. And then I'll keep the numbers nice and simple, so I'll put in 5 fluo-4 molecules. So when we first just dump the fluo-4 molecules in to this test solution, then of course initially none of the fluo-4 molecules will have calcium bound. However, what will now start to happen is the forward reaction will occur, i.e. some calcium ions will start to bind to fluo-4 molecules. Okay? So let's draw this happening. So what it will go to is something like so. Okay, so let's have whoops, no, I need to do this in colour. Let's have two of the Fluo-4 molecules getting bound to calcium ions. Okay, so here are our Fluo-4 molecules. Okay, now let's have two of them bound to calcium now, like so, and then the other 8 calcium ions will still be in free solution. Okay, right, there we go. So, basically, what is happening at this stage is that we're getting forward reaction occurring. So calcium is reacting with the Fluo-4 molecules to create these Fluo-4 complexes with calcium bound. Now, of course, the reversible reaction occurs as well. Fluo-4 with calcium bound, these complexes here, can break apart back into calcium and Fluo-4. Okay, so as soon as you actually have some Fluo-4 calcium complexes, what will happen is you'll start to get the reversible reaction, well, the reverse reaction occurring as well. So these will start to fall apart. So you've also still got some calcium ions free and some Fluo-4 molecules free. So what you're going to actually have now is you're going to have some forward reaction occurring, i.e. some of these Fluo-4 molecules will be binding to calcium ions and forming new Fluo-4 calcium ion complexes, and then you're also going to be having the reverse reaction occurring where calcium ion Fluo-4 complexes are going to be falling apart. And at the moment now, it will depend on what the relative rates of them basically are. Okay, now basically, let's say that at the moment, the rate at which we are forming new Fluo-4 calcium complexes is still greater than the rate at which they're breaking down. So maybe what it will go up to now is it'll go on further, and we'll end up with 3 of these Fluo-4 calcium complexes. So let's show these now. Okay, and I'll just put all the Fluo-4 molecules. So maybe we'll now get to 3 Fluo-4 calcium complexes, and then we've got the 7 calcium ions that are still free. Okay, right. And let's say here we now get to equilibrium, i.e. the rate at which these Fluo-4 calcium complexes will be breaking down is the same as the rate at which you'll be making new Fluo-4 calcium complexes. Okay, so let's say on this one here, we got one of these Fluo-4 calcium complexes breaking down in a second, and then we built 2 new ones. Okay, so let's say this one combined with this one combined with this one, but this one broke apart. Then that would give us this overall scenario. And the reason we moved, basically, was because, as you can see, the rate at which we're forming them, we formed 2 new ones and we broke down 1. At that stage, the rate at which we were forming them was faster than the rate at which we were breaking them apart, and therefore we moved towards a higher concentration of the Fluo-4 calcium complexes and a lower concentration of free calcium and Fluo-4. However, let's say now we are at equilibrium because the rate at which these break down is going to be the same as the rate at which we form new Fluo-4 calcium complexes. Okay, so basically we can say that there is some rate constant for the forward reaction and there is some rate constant for the backwards reaction, usually given K-1 like that. Okay, and the rate of the forward reaction will be K1 times the concentration of Fluo-4, which is free within the cytoplasm, okay, times the calcium concentration, which is free within the cytoplasm. And that's very important, that it's not the concentration of every calcium ion in here. You don't go through and look at every calcium ion, you only look at the free calcium ions, and you only look at the free Fluo-4 molecules, okay? And if we want the equilibrium concentrations of Fluo-4 and calcium, then we need to say that this now needs to be equal to the rate at which the backwards reaction is occurring, i.e. the rate constant for the backwards reaction times the concentration of Fluo-4 calcium complexes. Okay, now this then gives us the equation for an equilibrium, basically, because we can take this negative rate constant over to the other side and have K1 divided by K to the negative 1 is equal to the Fluo-4 calcium complexes divided by the concentration of Fluo-4, which is free, times the calcium concentration. Okay, now people basically call this ratio between the forward and backward rate constants, they call that the affinity constant. Okay, so this is called the affinity constant. So basically, what this equation tells you is that at equilibrium, the concentration of Fluo-4 calcium complexes, which is the number of Fluo-4 calcium complexes within 1 litre, basically, 1 decimeter cubed. Okay, and I like to subscript this equilibrium. These are the concentrations at equilibrium, divided by the free Fluo-4 concentration at equilibrium, times the free calcium concentration at equilibrium, that this will always equal a constant, basically. Okay, right. So what we're going to use is we're going to use this to find the occupancy equation. So let's remember what we're trying to find. We are trying to find the fraction of Fluo-4 molecules that will be present as Fluo-4 calcium complexes. Okay, so we want to find alpha. We want to find the fraction of Fluo-4 molecules that are within Fluo-4 calcium complexes. Okay, so this is going to be the concentration of Fluo-4 calcium complexes, that bit's obvious, at equilibrium, divided by, and this is the bit where people generally go wrong, they usually say, well, it's obviously divided by this. No. What does that give you? That tells you the number of, well, the concentration of free Fluo-4. Okay, that does not give you the total concentration of the total concentration of Fluo-4 molecules within here. Okay, what we need to do is add up the concentration of free Fluo-4 molecules, and we need to add it to the concentration of Fluo-4 molecules which are in Fluo-4 calcium complexes. Okay, and that will give us the total concentration of Fluo-4 molecules within here. Okay, so remember, this does not mean the total number of Fluo-4 molecules. It means the total number of free Fluo-4 molecules that don't have calcium bound to them. We want the total fraction that are present within Fluo-4 calcium complexes. So we need to take the number that are in Fluo-4 calcium complexes and divide it by the total number, which is the number that are in Fluo-4 calcium complexes and the number that are free. Okay, and now what we do is we use this equation here to replace the Fluo-4 calcium complex concentration at equilibrium in this equation here. So basically we can rearrange this equation to give us that the Fluo-4 calcium concentration at equilibrium, okay, is equal to the affinity constant, Ka, times the concentration of Fluo-4, which is free at equilibrium, times the concentration of calcium at equilibrium. Okay, so this is the concentration of free calcium, not the total concentration of calcium. Although, as we're going to see, we're going to later replace it with the total calcium concentration, but that's an approximation. That's where the beautiful, rigorous model is taken to the limits of practicality, basically. Okay, and I'll explain the justification for why that's an okay approximation later. Okay, so we're now going to stick this in place of the Fluo-4 calcium complex concentration, and what we'll get is that alpha is equal to, sticking this in on top, we get the affinity constant times the free Fluo-4 concentration at equilibrium times the calcium concentration at equilibrium. Okay, we don't need to replace this, so we leave that there. So this is the Fluo-4 concentration that is free at equilibrium plus, and then we stick in this, Ka times the Fluo-4 concentration at equilibrium times the calcium concentration at equilibrium. Okay, and you'll notice that we can cancel something now, which is absolutely beautiful, because we didn't know, we had no hope of knowing this number. So it's beautiful that that number now will just cancel off, basically. So we can cancel that, that, and that. And what this equation finally becomes is then that alpha is equal to Ka times the concentration of calcium, which is free at equilibrium, divided by, we have a 1 here. So remember, we didn't just cancel that off. What we did is we divided by the concentration of Fluo-4 that's free at equilibrium. So we divided the top by that to get rid of it here, and then we divide the bottom by that to get a 1 here, and then we get 1 plus the affinity constant times the calcium concentration that is free at equilibrium. Okay, so basically, if we know this constant, and this constant, the affinity constant, is something that you can look up in a textbook, it is known basically for the binding of calcium to Fluo-4. It's just some constant, and someone long ago has worked that out for you. Okay, so you can find that number in the textbook. All you then need to know is the free concentration of calcium at equilibrium, and then in principle you can work out the percentage of the Fluo-4 molecules that will have calcium bound to them at equilibrium. Okay, and that's what this alpha is. And this equation is called the occupancy equation. Now, we are going to make one little modification, because basically we don't know what the calcium concentration at equilibrium is. And we don't want the calcium concentration at equilibrium. What we want, remember, was the calcium concentration initially in the test solution. So before you ever added Fluo-4 molecules, you had a certain concentration of calcium in this solution. That's the one we're interested in. Okay, we then added Fluo-4 molecules, and some of these calcium ions bound to Fluo-4 molecules. Okay, and then were no longer free calcium ions. So this number, the calcium concentration at equilibrium that is free, is actually slightly lower than the calcium concentration that was originally within our test solution. Okay, strictly speaking, the number we put in here should be the free concentration of calcium at equilibrium, but we are going to use the approximation that that is approximately equal to the concentration of calcium that was originally within our test solution. Now that is a valid approximation because generally you will have an absolutely huge number of calcium ions compared to the amount of Fluo-4 you put in. Okay, so generally, hardly any of the calcium ions will actually end up bound to Fluo-4 molecules because there actually is very few molecules of Fluo-4 in the solution. So the number that you actually lose out of free solution by binding to Fluo-4 molecules is negligible. So we can approximate to all extents and purposes that the concentration of calcium that is free at equilibrium is the same as the concentration of calcium that was originally in our solution here. Okay, that now gives us, just to get another piece of paper, that now gives us the equation that alpha is equal to the affinity constant times the free concentration of calcium that was originally within our test solution divided by 1 plus this affinity constant, which tells us how much calcium wants to bind to Fluo-4, basically, is what this tells us. Okay, times the concentration of calcium that was originally free within our solution. Now, people don't generally work with the affinity constant, okay? Instead, they generally work with something called Kd, which is called the dissociation constant instead. And basically, there's a very simple relation between the affinity constant and the dissociation constant. So basically, this is how the dissociation constant is useful. The dissociation constant is basically just the reciprocal, i.e. the multiplicative inverse of the affinity constant. Why is this nice? Well, basically we can divide the top and the bottom of this equation by the affinity constant, and then what we'll get is on the top we'll just get the calcium concentration that was within our test solution originally. Then on the bottom we'll get 1 divided by Ka, which I've just said we're going to call the dissociation constant, and then here we'll just get plus the concentration of calcium in our test solution. So this gives us the concentration of calcium in our test solution divided by Kd plus the concentration of calcium in our test solution. Okay, and that's a very nice simple equation. Right, now, we'll call it there for this video, and in the next video we'll begin by discussing an interpretation of the dissociation constant. We'll then discuss the units of both the affinity constant and the dissociation constant. Okay, so see you in the next video.